All right, chemistry class, let's look at the final chapter for semester 2. We are looking at chapter 20, which is all about electrochemistry. So remember that electrochemistry is basically taking chemical energy, chemical potential energy, chemical kinetic energy, or chemical energy, and turning it into kinetic energy or electrical energy. Okay, so you're taking basically a chemical reaction and allowing that chemical reaction through the transfer of electrons to then produce electrical energy. We capture that flow of electrons and then we can make something operate. We can make something move and have then kinetic energy. So it allows us to take the chemical reaction and transfer that type of energy into a form of energy that we can then use through electrochemistry. So let's look at, first of all, let's look at our cell, our galvanic cell. If you remember, we looked at a galvanic cell and we set it up different ways, but one way we can set it up is by taking and dividing it into two halves. Remember, this in the middle here is going to be something that's going to divide the solution so they don't mix too much, but it still allows the flow of charges back and forth. So that is some type of semi-permeable barrier, okay? On one side, we are going to have a metal in solution. On the other side, we're going to have another metal in solution. On the left side, at least usually traditionally when it's drawn, the left side is going to be what is called your anode. And your anode is where the oxidation is occurring. So let's say, for example, I think the example we may have used was zinc and copper. So the anode, this electrode, this piece of metal here, that electrode is now called the anode. That's where oxidation is occurring because these zinc atoms are going to be losing electrons, and that zinc atom then is going to go into the solution as zinc ion, 2 plus. It actually is going to lose 2 electrons. Each atom is going to lose 2 electrons. Of course, we have this connected up through a wire, and then our device, whatever device we want to operate, if we have like a bulb here or something. Oh, that is a terrible looking bulb. Sorry. Okay, a bulb. We have a bulb here. In order to make that bulb work, we want those electrons to flow through that bulb from one side to the other. On the other side, you've got copper, and that copper is where you are going to have the reduction. This electrode, this piece of metal, is called the cathode. And in this case, these electrons are coming from the other side, the zinc side, the anode side, and these electrons then are flowing down. And the ions that are in the solution here are going to bump into that piece of copper metal, pick up those electrons, and turn into neutral copper atoms. So over here in this solution, we've got zinc ions that are building up. And over here in this solution, we started with copper ions, but those copper ions are turning into neutral copper metal atoms. So these ions, the zinc ions over here, were produced originally because we, in that solution, we put a compound like zinc sulfate. So you might have other ions in here like sulfate ions. Over here, we would have maybe copper sulfate. So we'd have sulfate ions over there as well. But it's the zinc and the copper ions that are most important to us. On this side, on the anode side, where the oxidation is occurring, zinc metal atoms are losing electrons and turning into ions. Those ions go into the solution. Over on the other side, because of the flow of electrons from left to right, these copper ions are picking up those electrons when they bump into the copper metal, and they will then turn into copper atoms, metal atoms, neutral copper metal atoms, and deposit themselves on this copper metal. So over on this side, you're going to see loss of mass. This zinc bar is going to get smaller and smaller and smaller. Okay, you're going to have more and more zinc atoms lost into the solution. Over on this side, you're going to see an increase. You're going to see additional. You're going to be gaining mass over on this side. Okay. You should be able to write the half reactions for this. Zinc is turning into zinc ion, which is 2 plus, which means it lost 2 electrons. Over on the other side, we've got copper ions that are picking up 2 electrons and turning into copper metal. Okay? So we've got your anode, your cathode, half cell. You should know what's happening on both sides. And you should be able to draw this electrochemical cell diagram. Now, I drew this and told you that the left side is oxidation, the right side is reduction, which is usually the way that we're going to draw it. But if you were just given half reactions, if I just gave you half reactions, like if I just told you zinc 2 plus picking up 2 electrons, turning into zinc metal, and copper 2 plus picking up 2 electrons, turning into copper metal. These are both reduction reactions. Both these are reduction. You might be given both of these, and both of them look like they're picking up electrons. But if you put them together in the same galvanic cell, they both can't gain electrons. One of them has to give up electrons, one has to gain electrons. So the one that has the higher standard reduction potential value, and you'll be given a chart. You just look at the chart and compare these two half reactions. Whichever one has the higher value is the one that is going to win the tug of war on the electrons. That's the one that's going to gain. So in the chart, if you look at it, you would see that the copper ion has a higher standard reduction potential than the zinc. So this is the one that's going to be reduced, not the zinc. The zinc is going to be oxidized, and so this zinc ion, that's not the half reaction that's going to occur. It's going to be this one up here. Okay? If you want to calculate then the E cell, the voltage, the push, the force that is behind these electrons going through this galvanic cell, you would simply take the two values from the chart, straight from the chart. Always take the higher number. This is the larger number here in our example, the copper, minus the smaller number as far as the standard reduction potential. It's always larger minus smaller, or it's always cathode minus anode. Always, always, always. Okay? So we talked about standard potentials. The cell notation is basically taking this galvanic cell, this whole diagram right here, and writing it in shorthand. So we draw two vertical lines. That represents the barrier here in the middle. And on either side, we have ions, a solution that has ions in it. On the left, we've got our zinc 2 plus, and you might see a concentration there. On the right, we've got our copper 2 plus, maybe with a given concentration. And then the metal electrode, we would be telling ourselves what metal electrode is being used, and maybe put a little S there to show it's a solid. Okay? That tells you everything you need to know. On the left, this is always oxidation. This is always reduction. This is your anode. This is your cathode. And there you go. Okay? One other thing I forgot to mention. In order to keep neutrality on both sides of this galvanic cell, since on the left side you're going to have a buildup of positive ions coming into the solution, you're going to have more and more of these zinc ions building up on the left, and you're going to have a loss of positive ions on the right. These copper ions are turned into neutral copper atoms. You need to maintain neutrality in the solutions. So there's going to be a flow of charges. The positive charges, since there's more and more positive charges being built up on the left side, they're going to flow through the semi-permeable membrane from left to right. Okay? And the negatives are going to flow from right to left to try to keep the two sides neutral as far as the charges in the solutions. So let's look at some of these questions down here. Let me just check to make sure I covered everything. I think so. All right. Use the reduction potentials in the table below to determine whether the following reactions are spontaneous as written. So if you calculate, when you calculate the E cell, if you get a positive number means the reaction, the galvanic cell will operate. It will be spontaneous. Okay? If E cell is greater than 0, then it is spontaneous. In the previous chapter, we talked about delta G. If delta G is less than 0, it is spontaneous. Okay? Delta G is free energy. So that means that there's energy that is being released if that delta G is negative. Energy is being released from the reaction, and that's spontaneous. But E cell talks about the push behind the electrons in the electrochemical reaction. If E cell is positive, that means there is a push behind those electrons, and the electrons will flow from left to right. So you're looking here, and you look at this, and you say, is there going to be a positive E cell? Well, you look at the setup here. We are showing that copper 2+ is turning into copper neutral, and that Fe is turning into Fe2+. So the two half reactions would be copper 2+ turning into copper by gaining, sorry, it'd be over here, by gaining 2 electrons. And then the iron would be losing 2 electrons, turning into 2+, according to this reaction. Well, then I look at my standard reduction potential. In this situation, is copper really going to gain the electrons over iron? So I look, is copper 2+ above iron 2+ on the standard reduction potential? Yes, it is. And so this is exactly the way it'll operate. Copper will gain the electrons, iron will lose them. The reverse reaction would not occur. If they gave you Fe2+ and copper turning into copper 2+ and iron, that would not occur. This would not be a spontaneous reaction, because you just flipped it around. This is saying that iron is going to gain the electrons, but it's not. And it's saying that copper would lose the electrons, but it won't. That's not the way it's going to happen. Okay? And then here, if a cell is constructed in which the following pairs of reactions are possible, what would be the cathode reaction, the anode, and the overall cell voltage? So here, you're going to just compare these two. You're going to find these two reactions on your standard reduction potential table. Look it up on the internet if you need to, or look back in your the formula sheet, and you're going to compare these two values. The larger one, whichever one is larger, is going to be your cathode. Okay? The large value is your cathode. The anode is your smaller value. So whichever one of these is larger, that's the one that actually is going to gain electrons. Whichever one is smaller, you would actually see the reverse reaction occurring. And I don't know which one is larger, which one is smaller. And then you would, to find the overall cell voltage, you always take cathode, and what I mean is the E of the cathode minus the E of the anode. It's always large minus small. Okay? So practice with these here and check your answers down below. All right? As always, you got to let me know if you got questions. You got to struggle through these, work through these, make mistakes now so that you can figure out what you're doing. And hopefully this is a great review for you guys, and hopefully this will help you perform very well on the final exam.